the team says there's a bunch of like, if you go into the Hyperloop Instagram, I actually followed a bunch of like other teams.
So this right here is the
My secrets. They do. They actually posted their feature. Hey guys. Like I feel like, you know,
I forgot about the workshop. The workshop's gonna be hosted in the other room.
I'm lazy to get off the ground and channel to channel, but I'm having trouble coding.
oh,
It should be simple.
Yeah.
Already, you know, but
that's fun. It's fun stuff.
this is like a piece of cake.
Piece of cake.
Because I just needed to,
Let's do that then. Yeah.
I just needed program in order to go back and forth to the direction of it, back and forth, and the timing.
All right, Arya, on you.
Hello.
Okay,
Who put this in?
I'm good to go.
Let's do it.
All right. Okay. Hi, everyone. My name is Arya. I'm the consult team lead this semester, and welcome to the Flow Simulation and Motion Study Workshop. Today, we're going to be talking about three main things. We're going to be talking about how to, how to do flow simulations on SOLIDWORKS, how to run stress analysis using simulation on SOLIDWORKS, and also how to evaluate the motion of an assembly by using a motion study. And all of these functions are found in SOLIDWORKS, and they come in real handy when you're trying to understand how a part is going to work, especially how it's going to interact with other parts in a greater assembly. So first thing is, well, what is a flow simulation? A flow simulation is basically an analytical tool, right, that you can use to analyze how a certain part or object is going to behave when it travels through a fluid, whether that be something like water or air, right? And basically, from that understanding of the interactions between the moving fluid, the surrounding fluid and moving object, we can understand some really key characteristics of the object and its interactions, such as pressure, velocity, and drag force and whatnot. And this is especially very essential for CPP Hyperloop and when we're making the pod, because we want to make a very aerodynamically efficient pod, as you know, and make it as aerodynamically efficient as possible. So this comes in handy, and we will be going over three different geometries and three different geometric shapes and see which one is the best fit for perhaps an outer body of a vehicle, maybe like a Hyperloop pod. Then then we're going to be talking about stress simulations. We are not going to get too much in detail about like what different types of stresses there are. There are a lot of different stresses, and there's bearing stress and bending stress and everything. But what ultimately what we're going to be doing is we're going to be using stress analysis on SOLIDWORKS to understand what regions of the part are the weakest when there is a load that is exerted on that part. So if you look at this SOLIDWORKS body, you can see that the weakest point in this kind of two welded rectangular parts is that cross-sectional area, which is highlighted in red and a little bit in yellow. That is the point where this part may break if there is excessive load. And on the left, you can see what can happen when there is overexertion of stress, more than what the system can handle. It can lead to catastrophes. And that's not just in the case of construction, but in the case of automobiles and even the case of a Hyperloop pod. And then finally, we're going to be looking at a motion study. And a motion study is basically a motion capture video that kind of highlights the importance of the assembly when it's moving. So as you know, an assembly has a variety of parts, and they all do their own functions. And if you want to show someone how your product is going to work, you want to kind of show it in motion, show how all the parts are going to interact to accomplish a certain goal. So as you can see here, like a screwdriver, right? This is how exactly it's going to work out. So, you know, if this was a stationary, then maybe you might question how is this going to work, but in motion, you know exactly how it's going to work and how it's going to be used. So we're going to be studying that on SolidWorks as well. So any questions about any of this? We're going to move on to SolidWorks after this. Okay. All right. Let's see. Okay. Okay. So first we're going to look at a simple triangle, right? Now the triangle's nose is actually, you know, in the X direction, as you can see here. And that's going to be important when we run the flow simulation, because that's the direction that this object is going to be moving. So what we want to do is first, if you have SolidWorks open, see if you have a flow simulation option here under the taskbar. If you don't, then go to SolidWorks add-in and install the SolidWorks flow simulation. You should see this option under SolidWorks add-ins. If you don't, then when you downloaded SolidWorks, I think you were supposed to choose a flow simulation option. So maybe if you go to their website and try to re-download, make sure to click on flow simulation. But I think for the most part, you should see this option. And once you click that, you should see this pop up. Right now, what you want to do is you want to go to Wizard. And basically this new screen pops up. Can you guys see the Wizard project name mini screen? I think you can. Okay.
Arya, can you hear me? Ah.
Yeah, I can hear you.
Okay, so we have to mute you for a second, but we cannot really talk to you because the echo is horrible. Oh shit.
Okay. Let me know when that's fixed. Okay, seems like we're good. All right, so you can see the project name screen, right? Just want to confirm one more time. Seems like you can. I can see the screen from here. Okay, so basically you can give it a project name and you can give it comments. This is just for your own use, just to kind of basically you know, structure your analysis in a way where you have all of these different projects ordered based by name and comments, and you can use that. After that, press next. Now here you choose a unit system in which you want to run your flow simulation. So if you're going to be using English units, choose IPS. If you're going to use metric, choose SI. Since most of our calculations have been in IPS, we will choose that. Here, these are units. Here you can change the decimal place. So this kind of gives you a more precise value. But these are pretty good for at least for our case, because these go up to the thousandth place. Some go to like 10,000th place. But yeah, you can just leave that as it is. After that, you want to choose external for your analysis type, because ultimately that's what this analysis is how the flow is going to kind of interact with the moving object. So you would choose external. Here you have other physical features that you can choose from. We're not going to be using this in our example, but you can click on gravity. There's rotation, if there's any rotation involved with the moving body. And then there's other thermal stuff like heat conduction and radiation. But you can leave that blank for simple analysis. Now you're gonna get an option to choose the type of fluid that this object is immersed in. For the most part, we're gonna choose air, but you can choose other stuff like water as well. You wanna leave the flow type as laminar and turbulent, because we don't really know whether there's gonna be a transition from laminar to turbulent. If you've taken fluid dynamics, or if you know a bit about aerodynamics, then you know that there's a transition that happens between laminar and turbulent flow. But since we're not sure whether this is going to be purely laminar or purely turbulent, just leave it as laminar and turbulent. So let the program decide what state the flow is going to be in. Here, you can choose the roughness. This is more for precise measurements. If there's a roughness on the surface of the body, that's going to change some of the values, but it's not that big of a deal, so we can leave it at 0. Okay, now here you want to give parameters for this study, and since we're going to be testing, since we're assuming standard temperature, standard pressure, atmospheric pressure, you can leave these as they are. The only thing we want to change is the velocity and in the x direction. Oh, let's say we can give like 100 inches per second. This is just a random value. So this is the velocity of the object in the x direction, and we'll keep velocity y and z 0. Oh, sorry, I just saw Chris ask that question. Actually, what you do is under flow simulations, you press wizard. So if you press wizard up there, it's kind of grayed out right now, but if you click that, this box should show up. Okay, yeah. So basically choose a velocity. This is going to be an instantaneous velocity or the maximum velocity in our case, because when the Hyperloop pod accelerates, it's going to go from 0 to whatever maximum speed it's going to have. You want to choose the maximum speed because basically using the maximum values, you're going to find like the maximum pressure, the maximum drag force and everything. So you always choose maximum. So in this case, we'll use 100. Okay, and we'll keep 0 in y and z direction. If this was in like projectile motion, then you can change the velocities in the y and z direction. But we'll finish. Okay, now this kind of box will show up, which is going to enclose the part. Now what you actually want to do is sometimes this box is going to be really big. So go to computational domain and make it smaller. And you don't really need to do this. This is just to save you kind of some time, because it takes a while for the simulation to run. And if you're going to kind of evaluate a smaller space, then it's going to be faster. So you can change the dimensions of that box. After that, you want to go to goals. Right click on goals and press insert global goals. Okay, now there are these parameters that are going to show up as options, and it's going to ask what you want to get out of the flow simulation. So for our case, let's look at the friction force in the x direction. Okay, we're going to check that box, and we're gonna press OK. So now you can see under goals, we see this GG friction force X in the X direction. Now you want to run the simulation. So there's a run button on top. Press run, press new calculation, or keep it on new calculation and run it. Do you guys see this screen? Okay. Good.
Yeah.
Okay, good. Yeah, so this is gonna be like another page that's gonna pop up, and it's gonna go through the iterations, and it's gonna give you a final friction force value. And here on the bottom, which is pretty cool, you actually see the iso lines of the pressure, right? And what you're actually seeing, and we'll kind of,
Oh yeah, we
yeah.
can't see it.
You can't see it?
Yeah.
On screen, bro. I think. Yeah, I think it was the wrong screen.
Okay, let me stop share and share it again.
Take this mouse with me.
Do
There
you see
we
it?
go. Yeah.
Okay.
Yay.
Okay, good. So yeah, so basically this is what's going to pop up once you press run. So here, there's if you click on this kind of like flag, this kind of box will pop up saying, and it will give you the list of goals that you've set for this flow simulation. And once the iterations are done, you'll get a final average value for friction force. But what's actually really cool is this isolines that are created for pressure. And what we're actually seeing is flow separation towards the end. Now, once there's a change in the color of the gradient or the isolines, and also you can see that there's a lot of turbulence at the tip of the nose of that triangle. Another thing that you can do, let me see. Should be able to see. Well, not sure why it's not popping up. Usually here you can choose some other, you can use this to look at some other plots as well. It's okay, we don't really need it. But yeah, it was good that you were able to see the isolines. Now, basically this is the average. Yeah.
So I tried to run the simulation on some beam that I had to run, but I don't see the image. I get some, I know that it says solver is finished, but I do not see the image of all the flows. Is it something that should appear automatically, or should I look for it in somewhere?
I mean, it depends. I mean, for me, whenever I ran it, it shows up. Sometimes it doesn't. Do you see this icon? Right now it's grayed out for me, but do you see it on your screen?
Yeah, I see it, but it's gray.
It's gray, huh? Okay. Are you able to at least see the list of goals?
I do not. I guess I'll just watch the video later, I guess. Or,
Okay. Yeah. So let me see. Let me see if I can go to results. It's okay if you don't see it, or if you're not able to see it, because there's a different way for you to look at it later. But here, the important thing is that you're able to see the actual friction force. And here it's a very small value just because of the dimension. This is a very small object. Like the dimensions are very small, but this is going to be the average friction force value. And of course, you want to lower this as much as possible. You know, if it's going to be aerodynamically efficient, it should be a smaller value. Now I'm going to stop share and go back to SolidWorks. Okay, so once this is once the simulation has ran, you should see a results bar here under project. Yeah, and then just click on it and press on cut plots. Right click actually, and then press insert. Okay, yeah, being a little once you press cut plots, make sure you choose a front plane. It's because that's going to be the cross-sectional area that we want to evaluate. And you can kind of, I think you can, let me see. I guess not, okay. What you can do is under contours, you can basically choose what type of parameter you want to evaluate. What we're going to do is we're going to evaluate velocity. And we want it to be a contour plot. Press OK. And here you'll see this. Okay. Now, what does this show you? So basically, what you're seeing is we're seeing constant, whenever there's a there is a similar color, that means it's constant velocity. So wherever you see dark red, it's the same or close to the same velocity. Once you see a change in those colors, you begin to see a decrease in velocity in this case. So here you can see that in the beginning, there is some decrease in velocity towards at the nose, but more so there's a big decrease in velocity once you get to the end. And from fluid dynamics, what you want to look at is you want to minimize flow separation. So here you're seeing a very large flow separation once you kind of get to the back side of the object, because there's a really large gradient in velocity. You want to minimize that as much as possible. So you want to keep everything red. If everything's red, then you want to keep as much area close to the surface of that object red, or you want to have that transition very small, right? Because if there's flow separation, then that means that there's kind of like this void area towards the back, and which is going to basically cause a larger drag force from the front, because, you know, if you remember from your fluids class or from studying fluids, whenever there's a difference in velocity, you're going to see a pressure gradient build up as well. So you don't want to have that pressure gradient. So you want to basically kind of have a good amount of velocity everywhere to be equal, right? So that's basically what you do. And this kind of gives you a good idea of how to approach building certain types of models for aerodynamics. Now, I was going to go over 2 more of these. I think maybe I'll post it in the Hyperloop chat later on, because it's going to take a while and we still have to cover motion studies and stress analysis or stress simulations. So I'll kind of skip that for now, but you can look at the velocity contour plots that I posted under the Hyperloop Discord chat, and you can see the difference between this and the ellipse and a rectangle. So we'll see that later on. Any questions about flow simulation? Oh, sorry. Any questions about flow simulations? Okay. All right. So we can move on to stress analysis. Let's see. I might have to share my screen again. Could you see this beam, or I might have to reshare? Let me just reshare this. Okay. So you see this beam. Now this beam is just like a rectangular prism. Basically, it's nothing fancy. And we're just going to use this to kind of understand how to approach stress analysis in SOLIDWORKS, or how to calculate areas or regions with the most stress in SOLIDWORKS. And, you know, we can have very complicated bodies such as the chassis of a Hyperloop pod, but it's basically the same concept. So by studying this kind of cantilever beam, we will be able to, you'll be able to understand how to approach different, more complex geometries. Okay, so go to simulation and press on new study. Okay, and you should see the static option pop up. Make sure that's checked off. So we're going to do a static analysis study. Okay, and press OK. Actually, wait up. Before we start, if you have a point load, which point load means something like, let's say there's a certain object attached at a very small cross-sectional area on the surface of this beam, then that would be a point load or a point force. If it's a distributed force, such as like, let's say, the weight of an object on top of it or something like that, then you can do a distributed load. And if it's distributed load, then it's easy. But if it's a point load, then it's a little bit harder. So we're gonna approach both, and we're gonna see what distributed load and point load actually mean. So first, since we're gonna do a point load, we're actually gonna go to let's see. We're actually gonna go to sketch, and on the top surface of this, we're gonna make a sketch. And we're gonna kind of pinpoint exactly where that point load is gonna occur. You know, here we're just gonna do some at a random place. For instance, right here, let's say this is gonna be where the point load is at, right? So that's gonna be like a very, it's gonna be a one arrow type of force acting on that particular point on the beam. Exit the sketch, go to features, go to reference geometry and press on point. So this point is gonna, oh wait, right. Let me see. There you go. Right. Okay, yeah, so you want to click on the two lines that we've made in the sketch. And that's going to basically give you the center of those two lines. That's going to be where the point's going to be. That we're going to use that as reference for the point load. Now we can go to simulation, go to new study, and click OK since it's already checked off as a static analysis. Okay, now you want to choose a point of fixture. So if we're going to evaluate this as a cantilever beam or just like a beam, we want to have one side perhaps attached to a wall or to a certain or to another object. So we need to have it fixated, otherwise we can't run the analysis, right? Because if it's just like, you know, an object in space, you know, it's not going to create any bending moment, or it's not going to create any displacements, right? You need to have a fixated region. So let's say that this is attached to a wall. Go to fixture, go to fixture, right click, fix geometry. Okay, and choose that face. Okay, so now basically this is going to be like the fixed end of the beam. Okay, now what you want to do is go to external loads, right click, and press on force. Now there was also an option for torque, which also is considered to be, or which is similar to moments. So if you want to add moments to this, you can do that as well. But so you see, we're going to do distributed load first. I'm just going to click on the entire top portion of this beam. Now this is a distributed load, so the load is distributed evenly, even though it doesn't look like it. I guess it kind of does. There is a pattern. but it's going to be a distributed load. And let's set the force to be 100 newtons. Okay. So as you can see, the arrows symbolize force acting on the body. This is the green arrows, or the other arrows kind of show where the fixture is. Now you can run the study. Oh, almost forgot. Go to part, and you want to edit the material, and you want to choose a type, because this is how it's going to evaluate the displacement of the actual beam, because it needs to know the elastic modulus and tensile strength and stuff like that to give you a more thorough static analysis. So I'm just going to choose, let's go with something like alloy steel. Okay. So once you press OK, the color might change, just kind of mimic the color of steel. Now you can run the study. Okay. You guys can see this, right? So what this basically shows is that once there's a distributed load, on top of this, there's going to be some displacement within the beam. And you can kind of, you could have expected that, right? If you think of this as like an eraser, which is flexible, if you apply force on one side, it's going to bend in this fashion, especially when this other end is fixed. Now, from this, you can see that the von Mises stresses are stresses that we use in industry to kind of determine what the actual stress is. These are the stresses that are important when trying to understand whether this object is going to fail due to excessive load. So the greater the von Mises stresses, that means this is an area of high probability of failure. So you can see the end is going to be a much higher probability of failure, right? So, and then there are other graphs that you can use. For instance, strain. This gives you more of a analysis of strain. There's displacement, which this is actually pretty cool too, because this kind of gives you exactly how much it's been displaced by. And here it's kind of opposite, right? The red was towards the fixated end, and the blue was towards the free end, but now it's changed because the highest displacement is at the free end, and then the lowest displacement is near the fixated end. So that's pretty cool. Now we're gonna do another analysis, and this is gonna be a point load. I'm gonna delete this just so that we don't confuse ourselves or. I'm just going to delete this analysis and we'll redo it. Okay, so press new study, static analysis, press OK. Fixtures, we're going to use the same fixture, which is going to be right here. Okay. Now, for external loads, press on force. And now you want to choose this point. Okay. And we'll give this 100 Newton as well. Let me see. Oh, I see. Yeah. It does that sometimes. When you click on the point, it for some reason shows the force to be in the Z direction, but we want it to be in the Y direction. So you want to, if it's chosen as normal and it gives you that error, then go to select direction, and you want to choose an edge or a line that kind of is parallel to the axis of interest. So if you want the Y direction, then we can choose something like this. You choose this edge. And now you can see you can see point force exactly at that point. Now it's the same thing. We run the study, but first, again, we want to edit the material. This time, let's choose something else. Let's choose rubber. As you know, this is going to be a much more flexible. Right. Sometimes it might not work because not all of these properties have been evaluated. You can kind of, if you're going to be using this material, then you can kind of fill those in. But actually, let's choose maybe something that has those values defined. Here's ABS. This is a common printing filament, the 3D printing filament that people use. Apply. Now we can run this. We can run the study. Here we go. So it's pretty much the same as before. It's going to be a little bit different because this is a point force instead of distributed load. But again, you can see that the highest stresses are towards the fixated end. The lowest stresses are at the free end. And we can look at displacement, right? The color switch. And I don't know if you remember what the displacements were for the last analysis that we ran, but these are much higher just because, again, this is plastic, the other one was steel. So that was expected. But you can use this to kind of understand where the highest displacements are going to be and where the highest stresses are going to be. And if you have any idea of how to do stress analysis and find the maximum allowable stress and stuff, then this kind of gives you an estimate of whether the stress is actually going to surpass the maximum allowable stress for that certain material and certain part. So yeah, you can use this as a pretty handy tool. Any questions about stress simulation? Okay, all right. Now we can move on to motion study. And for that, I have a vise that we're gonna study. Now let me see, share screen. Okay, so this is a vise that I got from GrabCAD. So we're gonna kind of use this to do a motion study. See, I've done emotions. I did this in the morning, but we'll redo it so I can show you exactly how to do it. Okay, so let's go to motion. Let's do a new motion study. Okay, so what you want to do first is you actually want to go to simulation. Actually, no, SolidWorks add-ins, and you want to click on SolidWorks motion. Okay, you want to click on SolidWorks motion. So basically, if you do that, you're going to see a motion analysis option down here. Before there was just basic motion and animation, and those are useful too. But with motion analysis, you get a better understanding of how the particular parts are going to work. So press on motion analysis. Okay, now we're set to kind of evaluate this motion study. Now, if you know how a vise works, basically this is like a lever, right? And you spin this clockwise or counterclockwise. And as you spin it, this screw is going to move in a linear fashion, and which is going to bring these two clamps together, right? It's a very simple, vise. So how you want to kind of use this is we know how this body is going to work. So what we want to do is we want to go and put a motor, right? And this is where we're going to have the input torque or moment or whatever we're going to be providing to the actual object. So here in this case, we're going to be providing a torque here, right? So if you click on it, you can see that there is this clockwise directional torque that's being provided to the lever. Okay, and here you can change the RPM or the speed. You can change the frequency, but we don't really need to bother with that. Let's just keep it at 100 RPM to see what happens. That's pretty fast. Just keep it like that. Okay, and then press this. After that, you want to go to mates, and okay, I already have this suppressed, but you want to suppress the limit distance. And the reason why you want to do that is because the motion study basically uses the mates that you've constructed when you're making the assembly to kind of show how the parts are going to move. There are certain mates that you want to suppress because they might hinder the motion of the actual part. Like for instance, here's limit distance, right? This basically defines the distance between the two clamps. If we have that, if we don't suppress that, then it's going to stay constant, right? But if we suppress it, then the clamps are going to be able to kind of move alongside the screw. So you want to suppress that. It's already suppressed. Now, let me just make sure that I have everything. Okay, yeah. So now all you want to do is your end goal is to have these clamps kind of touch one another. So what you want to do is you want to press on this kind of whistle looking icon, which is contact. This basically simulates the contact between two bodies. Click on the first clamp, click on the second clamp. Okay. And press OK. Now, let's see. Press on calculate. Don't press the play button. Press on calculate. Because if you press the play button, it will work. But if you want to make any adjustments, you can make them here. Like there's the rotary motor. If you right click edit feature, you'll be able to change the RPM later on if you think this is too fast or it's too slow. But and then after that, if you click the play button, it's not going to provide you with those edits. At least when I tried it, it wasn't able to provide those edits. But if you go to calculate, every time you press calculate, it will reevaluate all of these parameters and provide you with a new motion study. So let's press calculate. Okay, you can see it move, right? Yep. So as you can see, as the lever is turned, the clamps get closer and closer. This is only a 5-second study. If you increase the length, let me see if I can do it 10 seconds. Yeah, it only goes up to 5 seconds. I think you might be able to change that by moving the top. The black diamond is basically what you use to kind of elongate or shorten your clip. Let me see if that works. It should. yeah, it works. And if you, as you can see, it gets closer and closer. If you run this for a longer period of time, then you'll be able to see this actually close in on itself. And you can also increase the RPM of the lever as well. But yeah, that's pretty much it. If you want to save this, you can press on save animation, and you can save it as a flash video, an AVI file, or an MP4 file, and save it onto your computer. Yeah, that's pretty much it for motion study. That basically shows, like this is a vice, it's simple. We know how a vice works, but this was more of a, if this was a complicated assembly and perhaps a newer assembly that people haven't seen before, then it's good to have a motion study done so you can kind of understand how exactly how it's going to work. So that's pretty much it. So we covered flow simulation, stress simulations, and motion studies. Any questions about any of that?
So we're good, Arya.
Okay, all right. So if
Oh,
no one has any,
In order to question.
okay.
When you're doing like a flow simulation on a part, how do you tell it to stop to actually the simulation? Like right now, the part that I was doing the flow simulation on is still, I guess it's under simulation, so there is that gray box around it, and I don't know how to tell it to stop doing that.
So it's so let me see if I understood you correctly. So it's continuously running. It's not like it didn't stop. The simulation didn't stop.
I don't know. I think it's stop, but yeah, the boundaries, the gray box that
Yeah.
it's around the object you're trying to do the simulation on is still there. And I don't know how to tell it to go.
Based on my experience,
Huh?
based on my experience, you can't get it.
No?
I tried leaving the study, right? And I came back every time. Yeah, once you start to get
Josh said that once you start, you can go back. Is that true?
I really don't.
Let me see if I kind of know what you're saying.
Arya, basically,
Yeah.
it's like, when you first start the flow simulation study, right? And you have the balance
Yeah.
of the where it's gonna be studying, like that little
Yeah.
dot around the, yeah. So once you stop the study, right? Let's say you're done with studying and you want to like go
Go back to sketch, let's say.
back to what it used to be without the study part. Like, can you disable the visibility of the boundary box? I guess that's what it is.
Yeah. I kind of got that from what he was saying. I think you can. I'm not sure how to though, because when you input a velocity contour plot, it takes up the entirety of that space.
Yeah.
I think you might be able to play around with it and see, but I'm not particularly sure how to. But when it comes to the analysis, it really doesn't cause problems because like you're still able to see the velocity profiles and everything. So
We were able to hide the boundaries, but I guess take all the information like sketch parts. It's still on.
Oh, that's just the different thing.
well, here you go. Go to computational domain and right click and hide.
Okay. This is the part. Okay. All right. So thank you.
We have found the solution to the problem.
Yeah. If you press computational domain, show, hide.
Thank you.
Yeah. So I guess it'll be a little bit more kind of clear to look at the contour plots now. But yeah, that's pretty much it. Any other questions?
Looks like we're good, Arya.
Okay, sounds good. And if any of you are using SolidWorks to do any of these, or just using SolidWorks in general and have any questions, hit me up on Discord and let me know and I can help you I can answer those questions. So
Thank you.
it's pretty much it for this workshop.
Thank you so much, Arya.
Right.
The best.
All right, see you, Chris. See you, everyone.
Bye.
Bye.